Hello and welcome to this second presentation relating to D'Alembert's principle. In the first presentation we outlined Newton's laws of motion and how D'Alembert's principle can be used to slightly modify the application of Newton's laws, showing you the reasons why we apply D'Alembert's principle. But in this presentation we're purely going to consider numerical problems. The exercises in this presentation are identical to those we solved using Newton's laws, but here we're going to apply D'Alembert's principle throughout.
And here's a brief overview of the presentation, outlining the problems that are going to be considered. So if you want to jump directly to the solutions, this slide shows you the approximate start times for exercise 2, commencing 8 minutes into the presentation, and exercise 3, commencing 11 minutes into the presentation. Unlike in the previous presentation when we solved these problems using Newton's second law, all these problems are now solved using D'Alembert's principle. Note the answers to the exercises are shown in the brackets here. And here's the approximate start time to exercise 4. That's in 30 minutes into the presentation. Again, this is solved using D'Alembert's principle. Answers shown in the bracket. And finally, the approximate start time to the solution to exercise 5, starting 18 minutes into the presentation. Answers in the bracket.
Let's first though consider some common errors relating to solving problems that involve force and acceleration. So the first point, forces on a body are only in balance if the body is in the state of equilibrium. If the body is accelerating or decelerating, then the forces cannot be equated to zero unless D'Alembert's principle is used and a compensating or inertial force applied to the body. Applying D'Alembert's principle does put the body in a state of equilibrium even though it's being accelerated. Second point, when drawing a free body diagram of all the forces acting on a body, do not include a force corresponding to the acceleration. Acceleration is a consequence of the forces applied to the body. It is not a force in its own right. Here are some common errors related to the action and reaction of forces. When problems involve weights that are hanging from cables, rope, string, etc., do not assume that the tension in the cable is equal to the weight, as this is only true if the body is in equilibrium. If the body is accelerating or decelerating, the tension in the cable will not be the same as the weight force. If the body is accelerating, then the tension in the cable will be different from the weight force. Let's review these common errors graphically on the following slide. So here's a free body diagram of a person, i.e. the body, standing in a lift. In this first scenario, the body could be considered stationary or moving with a constant velocity, but in either case, it's in the equilibrium position. In other words, all the forces acting on the body are in balance. So the upwards forces equals to the downwards forces. So this is a scenario where force P, the pull from a cable, for example, is equal to the weight force acting down. So this is a Newton's first law problem where the summation of all the forces must equal to zero for equilibrium. However, in this scenario, we have the body accelerating, in this case accelerating upwards. Again, we have a free body diagram, but we cannot now assume that force P, force in the lift cable, is equal to W. And that's because the accelerating scenario is a dynamic situation and the forces on the body are not in equilibrium. So this is a Newton's second law problem where the summation of all the forces must equal to ma, and that is mass multiplied by acceleration. Just for reference, here's a very brief recap from our previous presentation related to D'Alembert's principle. When applying D'Alembert's principle, we reduce a dynamic problem to a static problem where all the forces are balanced or in equilibrium. D'Alembert's principle only applies to body fixed axes, so our reference axis set here is actually fixed to the car and moving with the car. And to bring this situation into static equilibrium, we have to add what's termed the inertial force to our free body diagram shown here. Remember that the inertial force, which is mass multiplied by acceleration, ma, always opposes the change in motion. So in this particular case, we have an acceleration from left to right due to the applied force. So the car is increasing its velocity. So the inertia force has to oppose this change in motion. So it's opposing the direction of the acceleration. So now we've applied D'Alembert's principle to this situation. We use Newton's first law of motion, in this case in the horizontal direction as it's horizontal motion, to solve the problem. So Newton's first law we define as summation of all the forces acting on the body is equal to 0. Just note the positive notation used here. It's from left to right on our free body diagram. So in this case we have applied force P that we're trying to find, minus the resisting force R, in this particular case, opposing the motion, and of course minus our inertial force from D'Alembert's principle. That has to equal to 0 for equilibrium. We can then simply rearrange the equation to solve for the problem. In this case, we're asked to find the value of force P, so rearranging to find P is equal to ma plus R. So that's D'Alembert's principle applied to a body being accelerated in the horizontal direction. This recap here is applying D'Alembert's principle to a vertical change in motion. And again, we're going to analyse a dynamic situation as a static situation. In this particular case, we have a free body diagram, this time of a person in a lift. And again, the reference axis set we're using in this situation is a body fixed axis set, moving with the body. Our acceleration this time is vertically upwards, so we're increasing the velocity of the person in the lift in the upward sense. So our inertial force that opposes this change in motion, the ma force, which is again mass of the body multiplied by acceleration, is opposite to the direction of the acceleration. We're using D'Alembert's principle. Again, we simply apply Newton's first law, but this time in the vertical direction, as that's the direction of our motion. So summation of all the forces equals to 0. Of course, in this case, there's an additional force applied to the body because of the vertical motion, and that's the weight force, W acting down. To our positive notation used, when we summate all the forces, we have P minus W minus R minus the inertial force is equal to 0. And then we can simply rearrange the equation to find the required force. In this case, that's force P. That's a very brief recap. For further information related to applying D'Alembert's principle, I'll refer you to the previous presentation. Let's now revisit some exercises that we first reviewed in the previous presentation relating to Newton's laws of motion. This was exercise 2 from that presentation. A car having a mass of 1,000 kilograms is accelerated at a rate of 2 meters per second squared. We have to calculate the required accelerating force, shown here in the bracket. In the previous presentation, we applied Newton's second law directly, but in this presentation we're going to solve all the exercises considered using D'Alembert's principle. I would encourage you to start the presentation and attempt exercise 2 and apply D'Alembert's principle as we've outlined in the previous presentation. I will show the full solution on the following slide. Exercise 2, here's the solution, and we're using D'Alembert's principle. So the only difference between this solution and the solution in the previous presentation is that we're now considering a body fixed axis on the car, moving with the car, and so we add the inertia force on our free body diagram. From the question, the mass is 1,000 kilograms, the acceleration is 2 meters per second squared, but note this time we are applying Newton's first law. In the previous presentation we applied Newton's second law, summation of all the force equal to ma, but because we're applying D'Alembert's principle and included the inertia force on the free body diagram, which opposes the change in motion, this time its summation of all the forces equal to 0. In other words, we have taken the dynamic situation of the accelerating car and placed it into a static situation where the car is now in equilibrium. And as we're considering forces, we always need a positive notation stated, and in this particular case, positive notation for force and accelerations is from right to left, as shown here on the body fixed axes. So to this notation, we've got positive force P applied to the car, and we subtract from that the inertia force ma, and that must equal to 0. Rearranging, the applied force P required is the mass of 1,000 kilograms multiplied by the acceleration 2 meters per second squared. So 2,000 newtons or 2 kilonewtons is the force required to achieve the acceleration. If you compare that answer with the answer from the previous presentation for exercise 2, it's exactly the same. It's just the variation in the approach of the solution when we apply D'Alembert's principle. Exercise 3 from a previous presentation, a 5.3 ton aircraft travels across a horizontal runway. It has an acceleration A of 1.5 meters per second squared. We're asked to draw the free body diagram of the aircraft and determine the tractive resistance, the resistance to motion, labelled R here. We're given that the thrust, or the applied force to the aircraft causing the motion, labelled P, is 8.4 kilonewtons. The value of R is shown in the bracket here. Once again, we're going to solve this using D'Alembert's principle. I would encourage you to stop the presentation and attempt this question, extract the information from the question, sketch the free body diagram, state the appropriate equation, and solve for tractive resistance R. The full solution is shown on the following slide. So exercise 3 solution, and again solve using D'Alembert's principle. Note in the question that the mass of the aircraft is given in terms of tons, so 5.3 tons, I've stated that as 5,300 kilograms. The acceleration is stated as 1.5 meters per second squared, so that's my value of A, shown here on the diagram. And the thrust, or the applied force, is 8.4 kilonewtons. So P is equal to 8,400 newtons. That's shown here. In this particular case, we have to find the value of R, the resistance to the motion. Again, as I'm applying D'Alembert's principle, we have a fixed body axis moving with the aircraft, and I've applied my inertia force, the MA, opposing the acceleration, or the change in motion. I'm applying Newton's first law here because, again, the body is analysed as being in static equilibrium. And notice the positive notation this time is from left to right, as shown on the axis here. I'll let you review the solution at your own pace. The tractive resistance R is 450 newtons, and again that's the same value as we determined in the previous presentation, applying directly Newton's second law. Exercise 4, we have a person having a mass of 80 kilograms standing in a lift cage, as shown on the right here. We're asked to sketch the free body diagram of the person and calculate the reaction between the person's feet and the lift cage floor. We're given 3 loading scenarios here. Scenario A, when the lift cage is at standstill, so stationary. Scenario B, when the lift cage is accelerating upwards at 1 meter per second squared. And scenario C, when the lift cage is accelerating downwards at 1 meter per second squared. The answers are shown in the bracket. And once again, we're going to apply D'Alembert's principle. I'd encourage you to start the presentation and attempt this exercise. Just note in part A, when the lift is stationary, that is by definition a static equilibrium situation, so Newton's first law does apply there. For parts B and C, we'll apply D'Alembert's principle. The full solutions are shown on the following slides. Exercise 4, solution. For part A, when the lift cage is at standstill, this is a static equilibrium situation. The weight force W is equal to mg acts vertically downwards, and the reactive force from the lift cage on the person is shown upwards here. So this is a Newton's first law problem, where a summation of all the forces applied to the body in the vertical sense must equal to 0. Notice the positive notation used is upward forces positive. So for the free body on the right hand side, that would be positive P minus the W is equal to 0. The weight force is calculated from mg. We know that the mass of the person is 80 kilograms, and we always know gravitational acceleration is 9.81 meters per second squared. So we can calculate the weight force, 785 newtons. And rearranging the above equation, we can clearly see that the reaction from the lift on the person is 785 newtons. So exercise 4, part B solution. The lift cage is accelerating upwards at 1 meter per second squared. We're using D'Alembert's principle. So that means we have a fixed body axis shown here on the person, and we have the inertial or compensating force shown here, opposing the change in motion. So as the acceleration is up in this case, the inertial force is down. Again, notice that upwards forces and accelerations are considered positive. And for our free body diagram, again, as always, we have the weight force acting vertically down. We have the reaction P from the lift cage on the person acting up. As you mentioned, we have the inertial force or the compensating force. In this case, that's acting down. Applying Newton's first law, as we're using D'Alembert's principle, summation of all the forces equal to 0. In the vertical sense, that will be positive P minus the weight force, and this time minus the inertial force, is equal to 0. We know the weight force from the previous slide. The mass is 80 kilograms given in the question, and the acceleration is 1 meter per second squared upwards. So inserting the values and rearranging the equation, we find that the reaction force P from the lift cage on the person is 865 newtons. That's to achieve a 1 meter per second squared acceleration upwards.
Exercise 4, solution continued. This is now for part C, when the lift cage is accelerating downwards at 1 meter per second squared. On the right hand side we have our free body diagram, all the forces acting on the body. Note for part C, all downwards forces and accelerations are deemed positive. So we're going to apply Newton's first law because we're using D'Alembert's principle here. In other words, we have body fixed axes shown here, and of course the inertial force or the compensating force ma opposes the change in motion. So as the acceleration is downwards this time, the ma is upwards. So here's our Newton's first law, summation of all the forces equals to 0. With reference to the free body diagram, weight force W acts down, so that's positive force to our sign convention. The reaction force from the floor on the person, on the body, is upwards, so that's a negative force to our sign convention, so we subtract P. And the inertial force we can clearly see is upwards, so again that's a negative force, so we subtract Ma. Those forces must equal to 0. What we do now is insert the values. We know the weight force has been calculated previously as 785 newtons. We're given the mass in the question, it's 80 kilograms, and the acceleration is 1 meter per second squared. So inserting the values into the equation for weight, we're trying to find force P of the mass and the acceleration, and rearranging force P, the reaction from the floor on the person, on the body, evaluates to be 705 newtons. That concludes the solution to exercise 4C. And again, note this is the same value as calculated in our previous presentation when we applied Newton's second law directly to this particular problem.
And finally, here's exercise 5 from our previous presentation. We have a load, mass 1 ton, is to be hoisted vertically by means of a light rope. That means ignore the inertial effect of the rope. And the rope runs over a pulley and is accelerated from 0.2 meters per second to 0.5 meters per second. So we've got an initial and a final velocity here. The rope travels through a distance of 750 millimeters. We're informed that there's a resistance of 150 newtons. We'll assume that to be constantly acting. And we're asked to draw a free body diagram of the load that's being raised. We're asked to determine part A, the pulling force in the rope required to give the above motion. Part B, the work done, noting that work done is equal to force multiplied by distance travelled. And part C, we've got to calculate the average power required to accelerate this load, noting that power is equal to force multiplied by the average velocity. Answer is shown in the bracket. Again, we're going to apply D'Alembert's principle to solve this problem. It's mainly part A of this exercise we're particularly interested in. Parts B and C are unaffected by the use of D'Alembert's principle. I'd encourage you to stop the presentation and attempt exercise 5, but I'll show you the full work solutions on the following slides. Exercise 5, part A, solution. We're calculating the pulling force in the rope, labelled P in the diagram here. Extracting information from the question, the mass is 1 ton, so m is 1 ton. Converted that into kilograms, it's 1,000 kilograms. We know that the load is accelerated from 0.2 meters per second, so initial velocity 0.2 meters per second, to the final velocity v of 0.5 meters per second. The distance travelled vertically by the load s is 0.75 meters. There's a constant resisting force to the motion of 150 newtons. So label that as R 150 newtons. In the diagram here, I've extracted all the information from the question, the mass of the load, the initial and the final velocities, the distance travelled, and the resisting force. We will need to calculate the weight of the load W, that's mass times gravitational acceleration, G. Inserting the values, the weight force is 9,810 newtons. And note, as there's a change in velocity, there must be an acceleration applied. The assumption made here is that force R and acceleration A are assumed to be constant. Here's exercise 5, part A, solution continued. So the first thing we need to do is to calculate the constant acceleration, labelled A here. And we're going to use a linear equation of motion from our previous work, and that's v squared equals to u squared plus 2as. Rearranging for acceleration A, that's v squared minus u squared in the bracket, all divided by 2s. Inserting the values in the diagram on the right hand side, we have the final velocity, we have the initial velocity, we have the distance travelled. So that evaluates to A is equal to 0.14 meters per second squared. Exercise 5, part A continued. We're now going to apply D'Alembert's principle to on a free body diagram, our body fixed axis to the load, and our inertial or compensating force MA. Notice it applies downwards in this case because our acceleration is upwards. So again, opposing the change in motion. Calculating the pulling force in the rope. As we've applied D'Alembert's principle, then we can use Newton's first law. So summation of all the forces equal to 0. Note that P is the tension in the rope, shown here. From the body fixed axis, the positive direction in the vertical sense is upwards, and y direction shown there. So summating the forces, that will be a positive P is upwards, minus the weight force, W, that's downwards, minus the resisting force, because R is downwards, and in this case, minus the inertial force, MA, because that's also downwards. That equals to 0. Inserting the values from above, we know the mass of the load is 1 ton, so M is 1,000 kilograms. We've determined the acceleration on the previous slide, that's 0.14 meters per second squared. We know the weight force from the previous slide, and we know the resistance for the motion. Evaluating force P in the rope is 10,100 newtons. And again, that's the same value we calculated in our previous presentation when we applied Newton's second law. Exercise 5, this is part B, calculating the work done. Note that work done is force multiplied by distance travelled. I'll leave you to review this solution at your own pace. It's identical to that in our previous presentation. D'Alembert's principle doesn't affect this part B of exercise 5. And finally, exercise 5, part C, solution. This time we're asked to calculate the average power required. Just note that average power is equal to the force multiplied by average velocity. I'll let you review this solution at your own pace. It's identical to that in the previous presentation, but just be careful on calculating the average or the mean velocity as shown here. I hope this presentation has outlined to you the difference between applying Newton's second law directly or D'Alembert's principle to solving dynamic problems. So I hope it's been of use to you, and thank you for viewing.